Professor Etienne Pardoux is a renowned French mathematician and professor emeritus at AIS Marseille University. Internationally recognized for his pioneering contribution to stochastic analysis, while he is not known for his aphorism or philosophical quotes, his influence is reflected in the extensive citation of his work across mathematics and applied sciences. He is best known for introducing backward stochastic differential equation in a seminar 1990 paper with Shi Peng, a development that has become foundational in stochastic control and mathematical finance. His earlier work established key existence and uniqueness results for nonlinear stochastic partial differential equations. More recently, he has applied stochastic modeling frameworks to population dynamics, evolutionary biology, and infectious disease modeling. These contributions are further consolidated in his influential books published by Springer and Wiley, including Stochastic Partial Differential Equations, an introduction in 2021, Probabilistic Models of Population Evolution in 2016, and Markov Processes and Application in 2008. Join me and welcome Professor Etienne.
Okay, hi. Go ahead, please. Thank you very much for the introduction. I hope you can hear me. Okay, let me...
Yeah, I'm hearing, sir.
Let me share my slides. Okay, so I hope you see the slides. So I'm going today to talk about an epidemic model of malaria. It's a very, very recent work, which is not fully, okay, finished right now, but I will, oops. Excuse me. Okay, so okay, so thank you for the invitation, and let me try to share my thoughts. Okay, so as you know, and there has been already talks on the topic, on this topic in the conference so far, malaria is a very severe illness which affects currently around 250 million people in the world, mainly in sub-Saharan Africa, but also in South America and Asia. It is responsible for 600,000 deaths every year around the world. So, oops, malaria is a contagious disease, but unlike many other contagious diseases like smallpox, measles, etc., malaria is not transmitted directly from human to human. As you know, a susceptible human gets infected by the bite of an infected mosquito, and a susceptible mosquito can get infected when biting an infected human. So in this talk, we will present a new type of model for the propagation of malaria. This new model has two distinct features. Both, first of all, the infectivity of an infected human, but also the infected vector, mosquito, varies with the time elapsed since infection. And when a human, after recovery, loses his or her immunity, that is progressive. Not the loss of immunity is not instantaneous like in most models in the literature. So let me first present the model for humans. So we will be given a collection of pairs of random functions having the law of the pair lambda gamma of t, which denote respectively the infectivity and the susceptibility of the given individual at time t after its infection. We assume that lambda is 0 for t negative, and that lambda is non-negative for all t greater than or equal to 0. Gamma is between 0 and 1. We assume that the sup of lambda of t is bounded. Okay, in fact, I'm pretty certain that I can just assume that this random variable is integrable. That should be enough, but okay, it's not completely written so far, so I prefer, it's safer to say it's bounded. And moreover, I assume that the first time when gamma is strictly positive is after the last time when lambda is strictly positive. Okay, and okay, in addition, we are given other, similar quantities with a different distribution for the initial status of the individual, but I will not detail too much about that. Okay, let me explain on a picture what I was saying so far. So suppose here 0 here is the time of infection, then the individual might first be exposed. So the individual is not contagious, not infectious during the first interval of time. Then its infectivity increases up to a maximum, then goes down back to 0. Then there is usually an immune period. And in the case where there is loss of immunity, which is the case for many diseases, mostly not all, but many diseases, particular COVID-19, but also the malaria, then after an immune period, the susceptibility starts to raise again and may converge to 1 or may converge to something less than 1. Okay, so most typical models assume that the susceptibility of the individual at the end of the immune period jumps from 0 to 1 instantaneously, but we will not assume that. Okay, so now we consider a human population of fixed size capital N. To each individual, k between 1 and n, we associate its initial status, which is summarized in the pair lambda k0, gamma k0. Okay, I don't want to discuss too much about this. It's not too important. But okay, now the number of reinfections of the individual k on the interval 0t is given by this integral. So now qk is what is called a standard Poisson random measure on R2 plus, which means it's a sum of Dirac measures and those Dirac measures are located at random points. And the number of those points in any subset of R2 plus, any Borel subset, it's Lebesgue measure, and the numbers of points in these joint subsets are mutually independent. Okay, this is enough to characterize this Poisson random measure. Okay. Okay, so now you see you integrate over t, and when t increases, you encounter points of this Poisson random measure, and as soon as there is one point SU of this one Dirac measure in this QK is at a point SU which satisfies U less than or equal to the value just as S minus of this function, then the point is accepted and there is a jump of +1 in this, which means there is a new infection. Okay, now what is this mysterious function epsilon n k of t? Okay, there is a kappa, which is, okay, I will explain in a minute what is kappa, but it's not important. Now, what is important, the two important factors are the following. The first one, let me start with the last factor, which is the average is divided by NV, the average force of infection of the mosquitoes. Okay, the force of infection of the mosquitoes is exerted on the humans. Okay, this is the total force of infection of the mosquitoes. And then this is gamma, this is the susceptibility of the individual K. So as long as the susceptibility of the individual K is 0, then of course the individual cannot be infected. Okay, and the larger gamma, the more likely the person will be infected. Okay, what is this A and K of t? A and K of t is what I call the age of infection at time t of the individual, which means it's a time elapsed since the last infection. Okay, so it's t minus the largest s in 0t for which there is a jump of this function, which means that this is the time of the last infection on the interval 0t. And if there has been no infection, then this is 0, then this should be 0. Okay, so I think I've explained everything except I have not explained kappa. So N is a number of individuals. NV is roughly the number of mosquitoes. I say roughly because, as you will see, I have a I mean, there is demography. I mean, I'm not considering birth and death of the humans, but but I'm considering birth and death of mosquitoes. So the number of mosquitoes is not strictly fixed, but it's roughly NV. Okay, so kappa is the ratio of these two numbers, and we want to let both N and NV go to infinity, and we will keep kappa fixed. Okay, so by the way, just one word. I'm saying I'm not considering birth and death of humans, but you might object that, as I said on my first slide, malaria does kill individuals. So it's not fair to say there are no deaths of humans. Okay, but my assumption do not prevent that this function gamma could be 0 for all time with a very small probability. So when you pick, I forgot to say that at each new infection, this B and K of T increases by 1. So there is a new gamma Kj. So all the gamma Kj's are mutually independent. Okay. So when you choose a new gamma Kj with a small probability, that function will be 0. If this function is 0, it means that the individual will never become susceptible again. It will never be infectious again, so it does not play any role in the epidemic. And we could also decide that that could be the case of the deaths, those who die. Okay, so I have not explicitly written a status for death, but I could add it easily. Okay, now the total force of infection of the humans, which is exerted on the mosquitoes, is it is a renormalized total force of infection. So the total force of infection is this sum. Okay, you sum over all humans at time t. You take the infection age of the given individual, and you take its current infectivity. Okay, so of course, for many cases at any time t, for many cases this should be 0 because not everybody is infectious at any time. But okay, this is a general formulation, and then I'll divide by n, so I have a renormalized or rescaled total force of infection. And the renormalized total susceptibility, now this total susceptibility of the population at time t, it is quite similar, but I replace lambda by gamma. Okay, lambda is infectivity, gamma is susceptibility. So this is the infectivity which is exerted on the mosquitoes, and this is a susceptibility which is sort of the mosquitoes then attack those who are susceptible. Okay. Okay, so and then, as I said, those are ID copies of lambda gamma, and they are the ID copies of lambda 0 gamma 0. But I don't want to say too much about that. Okay, now this was enough for the stochastic model for humans. Now the stochastic model for the humans was what I call VIWI, which means varying infectivity and waning immunity. And the model for mosquitoes, it will be SI, which means susceptible infected, and VI, which is varying infectivity model with demography for the mosquito. So each mosquito has the infectivity lambda VI of T at time T after its infection. And the lambda VI, it should both it should be both L or both I. I'm very sorry. Okay, those are IID. And the initially infected mosquitoes have at time t the infectivity lambda v0 L of t, L between 1 and the number of initially infected mosquitoes. Okay, in addition, susceptible mosquitoes are born at rate nv times mu v of t, and each mosquito dies at rate mu v of t. Okay, instead of nv, if you like, I should maybe put the number of alive mosquitoes, but if I do that, I have the problem that I would have a critical branching process which dies out in finite time. So I don't want that. So therefore I fix the birth rate at a certain rate times the size of a population around which my mosquito population fluctuates. Okay, so each infected mosquito remains infected until its death. So there is no recovery. I mean, I talked with a medical doctor who has studied malaria, and he thinks that this is quite reasonable. Mosquitoes don't live very long, and they remain infectious for quite some time. So it's quite reasonable to assume this. Of course, I could change this assumption. It would not change too much the model, but okay, this is simplification which seems reasonable. And each mosquito gets infected at rate, okay, there is this factor 1 over kappa times the renormalized force of infection of the humans, okay? And the proportion of susceptible individuals in the mosquito population is given like this. So I first take all the initially susceptible individuals in the mosquito population. But okay, sigma j is a death time. So I multiply by the indicator function that that individual is still alive. And this means that the individual has not yet been infected. Okay, the Cnj of t is similar to the Bnk of t for the humans, except that here there is at most one infection, but this process is 0 and as long as the individual is susceptible and jumps to 1 when it is infected. Okay, and then I have to add those who are born after time 0, okay, because there is demography, so there are the deaths, but there are the birth times. So alpha j are the successive birth times of mosquitoes, and I'm sorry, alpha L are the successive birth time of the mosquitoes, and sigma L is the corresponding death time. Okay, so the interval of life of the mosquito L is alpha L sigma L, and the mosquito is susceptible as long as it has not been infected. Okay, and the infection happens at this rate, as I said. Okay, so in fact, I have told you the proportion of susceptible, but I have to tell you what is the force of infection of the mosquitoes. So there are 3 subsets of infectious mosquitoes. They are the initially infected, those who were infected at time 0. They are the initially susceptible who get infected at some time, and then those who are born after time 0 and who get infected. So the total force of infection in the mosquito population is the sum of 3 terms. Okay, so it's renormalized. I forgot to say the bar means I divide by NV, the size of the mosquito population. So I take, this is the total. The first term is the force of infection, the renormalized force of infection due to the initially infected in mosquitoes. The second term is the force of infection of those who were susceptible at time 0, but get infected at some time tau and j. This is the jump time of the process C and J. So it's the infection time of the individual J plus the same, but now for those who are born after time 0. Then, of course, the time of infection, of course, is posterior to alpha L, the birth time. Okay? Okay, so now I want to state the law of large numbers. So I claim the following. So I want to take the limit in the above model as both n and nv go to infinity, while the ratio nv divided by n remains constant. So our main result reads as follows. As nv goes to infinity, those four terms, so I have included the kappa inverse here and the kappa here. So, but forget about those, they are not important. I mean, you could take the simple case where this is 1 and then they disappear. Okay, so you have first the renormalized force of infection of the humans. The renormalized, no, I'm sorry, the renormalized, oops, sorry, I said something stupid. The renormalized total susceptibility of the human population is the first term. The second term is the renormalized force of infection of the humans, which is exerted on the mosquitoes. Then you have the proportion of susceptible individuals in the mosquito population, and then you have the renormalized force of infection of the mosquitoes, which is exerted on the humans. Okay, note that here concerning the humans, I talk about the renormalized total force of total susceptibility, while here for the mosquitoes, I talk about the proportion of susceptible. Because in the mosquito population, each individual is either fully susceptible, so susceptibility equals 1, or fully immune. Okay, so the renormalized total susceptibility in the mosquito population is exactly the proportion of susceptible individuals. So there is no reason to make, I mean, they are the same. Okay, so this quadruple converges in probability locally uniformly in T to these four deterministic functions, h x h of t, y h of t, x v of t, y v of t, where x h y h is unique solution of the system of equations which I will give on the next slide, while x v y v is an explicit function of y h. Okay, so you have four functions. Those two solve an equation, a little complicated equation, and these are given as explicit function of YH. Now, let me show you the formulas. Okay, so the pair XH-YH solves the following system. So here, okay, those lambda bar 0, lambda bar, these are just the mean, the expectation. Lambda bar of t minus s is the expectation of lambda of t minus s. Remember that lambda is random. I mean, there are many copies of those, but they all have the same expectation. So when I take the expectation, which I write here with the bar, I don't need to put any index because they have all the same expectation. And this is the expectation of the lambda 0, the initial infectivity. Okay, so this is a proportion. This is the initial proportion of infected individual at time 0. This is the expectation of the initial infectivity function, and then this. Okay, you see that this is an integral equation. This is an integral equation, and in addition, this is a complete. This is not such a simple. I mean, this is a explicit formula, but a little bit complicated. I will give it in a minute. But let me first comment about the first equation. Okay, so first of all, of course, XH, YH are deterministic. But what is random is both gamma 0 and gamma. These are random. So I have the expectations because I have to take the expectation of this complicated function of gamma, and here gamma 0. Okay. You see a big difference with this term here. This is expectation of lambda. It's just the first moment. So lambda in the limit, the random function lambda enters only through its first moment, its expectation, which is rather simple. While here, gamma enters the limiting equation, deterministic equation, through a complicated functional of gamma. And the reason is, okay, why does this exponential appear, this exponential function? You see, this exponential is, okay, suppose that an individual has been infected at time s. So this expectation is the probability that that individual has not been reinfected by time t. Okay, this is a probability of no reinfection, because you see when you look at those formulas, okay, that was here. Okay, here you see in the okay. I was looking at the equation for the limit as n goes to infinity of that quantity. Okay, that's why it's reasonable to have a look at this again. Now you see that this function gamma, I'm not supposing it as a function of its last argument. You can think that it is increasing. I have not assumed it increasing, but on my picture, I put it as increasing. It's reasonable to assume that it is increasing. But you see that this is the time since the last infection. As soon as gamma is strictly positive, you can be reinfected. When you are reinfected, then of course this is replaced by 0. This jumps back down to 0, and then this gamma is 0, because gamma, after infection, gamma is first 0 for quite some time. You see this picture. Gamma is 0 from the time of infection up to here, gamma is 0. Okay? So you see it is very important here. Oops. So I was here. What is very important is that, okay, as you see here, in fact, lambda, here we don't have the same game, because for a new infection to appear, you need gamma to be non-zero. For gamma to be non-zero, you need lambda to be 0. So first lambda becomes 0, and then maybe you have a reinfection. Here it's not the same situation. Here gamma is increasing, and then suddenly you have a new reinfection, and you go down to 0, and the individual goes back to, the individual k then contributes to this sum, and so only later contribute again to this sum. Okay, so I don't know whether this clarifies, but I insist that the presence of these exponential factors and the fact that I have those complicated exponential of, the fact that I have expectations of complicated functions of gamma is related to what I was trying to explain a minute ago. Okay, so this is the pair of equations for x, h, y, h, but I have to explain you what is this v of yhs, which enters here, 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 and here. Okay, so it shows up everywhere. Okay, so now the pair xv, yv is equal to the pair s of yh, v of yh, where s of yh is, you see, it's a rather explicit function of y shows up here and here, but it's a given function, it's explicit, and it's no problem. And in fact, not only it is explicit, but it is easily shown that it is bounded, for instance, in fact, uniformly in time. This is very nice. But the next expression is really a bit more complicated. Okay, you see now this v of yt. You see, you need first to have defined S in order to define V, okay? So V of yt, in fact, also is an explicit function of y, but much more complicated. First, you have to take, you have this functional which appears here, then you multiply by y. Okay, the first term is given, doesn't depend upon y, but this integral depends upon y. The second term depends upon y through that product of y by this S of y. Okay, so it's an explicit function, but not so simple. And that V again enters those this system of integral equations. So I insist also that this pair is not the pair XH, YH is not a solution of an ordinary differential equation. It is a solution of an integral equation, Volterra type integral equation. In particular, it has memory. Okay, it does not forget the past, unlike an ODE. Okay, so now, what do we prove? So I have stated a statement. What do we prove? We first prove that if I have a solution, then it satisfies a priori bounds on any compact time interval. Okay, this is very important because thanks to this, it's not difficult to show uniqueness, and also we can show existence by Picard iteration. But the Picard iteration is a little more tricky than uniqueness, because why any solution satisfies a priori bounds, it's not clear that the sequence in the Picard iteration satisfies the same a priori bound. So I use a modified Picard iteration to enforce those bounds, the same bounds that I was able to prove for the solution. Okay, anyway, and we can prove existence this way. So we have existence uniqueness of a solution to this system of equation. Now a very short, I will finish with almost finished, and then some other comment. I want to say one word about the strategy of the proof of the low-range numbers. So I will say a word about the model for the humans. Similar thing has to be done concerning the model for mosquitoes, but explain it for humans. In fact, the most complicated is the one for humans. So I have already showed you this thing. Okay, I hope you understand roughly what is this Poisson on the measure. Anyway, this is a process which jumps by one. Okay, this process counts the number of reinfections. This is the rate of new infection, and this is the age of infection, which plays an important role because it enters here. Okay. Now suppose I cheat. Suppose I cheat and I replace this annoying term, which is a complicated expression. Suppose I replace it by its limit as n goes to infinity. So as n goes to infinity, this quantity converges to yv of t, which is deterministic. So now, if we look at this, it is rather easy to see. Okay, now now you see I don't index those by n anymore. There is no index n. And in fact, you see that the B, okay, I forgot to say that the QK for various Ks are mutually independent. All the same law, IID, and they are independent. So now the B case, unlike the Bn case, in fact, the Bn case, you could argue that they are exchangeable. Okay, maybe I'm not sure you know what means exchangeable, but okay. Anyway, in particular, the laws of the various BKs for various Ks are the same. But here we have much more. Here we have the BKs are IID. In fact, the pair BK-AK are IID. And those, in fact, what is most important, those gamma K of BK of T, AK of T, those are IID, independent, identically distributed. Okay? It's obvious because you see the only, okay, so this is deterministic now, unlike here, it doesn't depend upon the other blast. And here, this QK, those are IID. The QK is the only force of randomness for BK. The only reason why BK is random, why all those things are random, is because this is random. Okay, but they are IID for various cases, so those are IIDs. And now there is so we construct an IID sequence to which we associate those quantities. Now recall that we have this. We have defined those, and those are the quantities which converge to the limit. Okay, there was a factor kappa inverse, but okay, it's not important. So we are taking the limit in those quantities. Now, if we cheat, we replace the BNK ANK by BK AK. Okay, everywhere, both here and here. Then I define what I call sigma tilde and h of t, f tilde and h of t. And now a classical functional law of large number tells us that locally uniformly in T, we have that those quantities converge, in fact, almost surely, better than my final result, which is in probability. I almost show convergence, and even locally uniformly in T. Okay, this is just the classical law of large numbers, except it's law of large numbers in some functional space of time. But okay, this is technical, it's not, but conceptually, it's rather standard. I mean, very classical. So now the two things that we need to show in order to conclude about taking the limit in Z pair, there are two things we still need to do. The first is that we need to check that you see what were the limits here in these low large numbers. We need to show that these are the same as the solution of our deterministic system of deterministic equation. Okay, this is some calculation. You just you multiply this by indicator B1 of t equals I, and the sum over I, the same here. And you just have to compute. It's not too difficult. You can show this. And the next thing we have to do is, of course, we have cheated because we have replaced the bar by the tilde. We have to show that the difference between the bars and tilde go to 0 and then goes to infinity. Now this is in probability. This is locally uniformly in T. So this is okay. This is some it's a computation which takes several pages, which uses essentially clever estimates plus Gronwall lemma, and you can show this. And once this is shown, then the result is proved. Okay, we have to do the same also for, I just explained for the human population, you have to do the same for the mosquito population. Okay, so good. So well, I want to finish with some, okay, I know that you are starving, you want to go to lunch, so I will not be too long. Now, I want to say one word about some work in progress, which we have not yet done. Okay, we hope to find out under which condition there exists an endemic equilibrium in this model. Okay, now, there is a result which we have proved for the usual epidemic VIWI epidemic model, not malaria, but not vector epidemic, but the usual epidemic. It is the case that the proportion of infected individuals at equilibrium increases when we increase the duration of the progressive loss of immunity. If you like, if you go back to the picture here, okay, so if okay, you could simplify by taking here, putting a straight line, okay, an oblique straight line, and then one. So if you compare between immediate loss of immunity and progressive loss of immunity, but of course with the same cumulative immunity, if not, we are cheating, then it is a fact. In fact, the first who noticed that are Tom Britton and Khalifi. Then it is a fact which we have proved also that this increases the proportion of infected individuals at equilibrium, which also changes the proportion of people you must vaccinate if you want to avoid epidemic. Okay, so we hope to be able to show the same phenomenon holds true in the case of an epidemic propagated by vectors. Okay, I went a bit fast. I forgot to say that this joint work with Othman Baghdadi from Oujda in Morocco, and I want to thank you for your attention. Okay, that's it. Thank you.